So let's quickly look at inhibitors for protein synthesis. Now, for illustration purposes, you all appreciate that protein synthesis is a process that occurs within ribosomes. Okay, within ribosomes. So basically what goes on is that we have three things involved. We have the messenger RNA, the ribosomal RNA, and the transfer RNA. So I'll just do a quick schematic illustration. So here is your messenger RNA. Of course, and it's of course carrying the codon that is necessary for protein synthesis. Okay. And for a particular peptide chain to be formed, we need transfer RNA. And transfer RNA is the one that must carry the anticodon that must match with the codon on the messenger RNA. Okay? So that when transfer RNA brings this anticodon here, it must be a match, or rather it must be correct. Okay? But of course this transfer RNA comes with it carrying a particular amino acid. So this code here codes for a particular amino acid that is carried by transfer RNA. Okay, but this whole process is checked and facilitated by ribosomal RNA. Okay, remember we talked about messenger, transfer, now for ribosomal RNA. So ribosomal RNA is in two units. We have what we call the 50S subunit that is on top here, 50S subunit, and we have a smaller one called a 30S subunit. Now, what happens is that this 50S subunit, the bigger one on top, and the smaller 30S subunit, these have two roles to play. When transfer RNA comes here to bring the amino acid that is necessary, it must find another transfer RNA already there, bearing as well another amino acid. And so a bond must be formed between these two amino acids here. Okay? A bond must be formed between these two amino acids. Now we know that when bonds are formed between amino acids, we have a peptide. And of course peptides eventually form proteins. Okay. So in summary, the 50S subunit is responsible for peptide chain formation. That's the role of the 50S. And the enzyme, as we always talk about, the enzyme that catalyzes this is called peptidyl transferase. Peptidyl transferase enzyme. So here, there's this guy called peptidyl transferase enzyme that catalyzes peptide chain formation. And so the role of 50S is simply to make sure that there is peptide chain formation. Drugs, therefore, that inhibit the 50S subunit, so we call them 50S inhibitors. 50S inhibitors simply inhibit peptidyl transferase and eventually inhibiting peptide chain formation. That is their mechanism of action, simply inhibiting peptide chain formation. Okay, and these drugs, examples, we have drugs that we call macrolides. We have drugs that we call lincosamides, and we have a drug that we call chloramphenicol. These are the drugs that inhibit 50S. What about the smaller 30S? What's the role of the smaller 30S? Because there's messenger RNA here bearing the necessary coding, 30S must check that the transfer RNA that has come here has the correct anticodon. Okay? Has the correct anticodon. So that the protein that is synthesized eventually after formation of these peptide bonds is the correct peptide bond. So 30S really acts as a checkpoint, analysis point. Is this the correct transfer RNA that has come? And so inhibitors of 30S inhibit what we call reading. Okay, there is reading that goes on here by 30S. That's a role of 30S, reading. Therefore, it results in misreading. When there is misreading, we expect an incorrect, unfunctional protein to be formed. Okay, to be formed. So 30S is responsible for reading, proofreading, and confirming that really the transfer RNA that has come is correct. And so examples of drugs that inhibit 30S are drugs that we call examples. We have one, aminoglycosides. Two, we've got tetracyclines. Now let's talk about this. So this is basically the mechanism of action of these drugs in a nutshell. And let's talk about these drugs in a bit more detail. Number one, we started with, we said which ones? 50S inhibitors. 50S inhibitors. And we said 50S inhibitors inhibit 50S subunit, bind to 50S subunit. So number one, in your mechanism you state that they bind to 50S subunit, thereby inhibiting peptidyltransferase, ultimately inhibiting peptide chain formation. Those are the 50S inhibitors. Examples of 50S inhibitors. One, we said which ones did we list here? Macrolides. Examples of macrolides we have erythromycin, azithromycin and clarithromycin. Macrolides are really just good for gram-positive microorganisms. We can't use them in gram-negative, they are not good. So we can use them for group B streptococcus, upper respiratory tract infections, pneumonia, and of course for community-acquired pneumonia, they are very good. They are very good drugs. Number 2, we said which ones? Lincosamides. Lincosamides. We really only have one drug here that is in clinical use, clindamycin. Clindamycin is a lincosamide. Not very widely used. They don't even have it in Zambia, but so you know. Third drug that is a 50S is chloramphenicol. Chloramphenicol. This is quite a dangerous drug. Has very bad side effects. Most commonly in babies. So I need you to look up the syndrome that chloramphenicol causes in babies. Okay? The syndrome. And then tell me in our next class. I'll ask you one by one. There's nothing like he has already answered. Tell me, great babies, tell me the chloramphenicol syndrome, how it's caused, Tell me that in our next class. Which should be today really. Should be at 15. Secondly, we look at the 30S inhibitors. Again, this bind to 30S subunit. Prevent reading, which results in misreading, and of course which results in formation of a dysfunctional protein. Second mechanism is that these drugs bind to 30S and prevent transfer and prevents transfer RNA from binding. So both of them are probable mechanisms. You can still get to know both of them. They are both correct. Examples of 30S. Number 1, I'm sure you have heard of tetracyclines. Examples: tetracycline is a class of drugs. So examples: tetracycline itself. Tetracycline is a drug itself. We have aminocycline, or for short it's called minocycline. Minocycline and chlortetracycline. Do not mistake this with the penicillins. Penicillins are penicillin. These are clean. Do not mistake this with this. So I don't want to hear people say cloxacillin is a tetracycline or tetracycline is a penicillin. No. Number 2, we have the class called aminoglycosides. Aminoglycosides, we have gentamicin, we have amikacin, we have 3 kanamycin, and 4 streptomycin. Okay, these are the aminoglycosides that we have as 30S inhibitors. Know them, know the names, know which one is a 50S inhibitor, know which one is a 30S inhibitor, understand the mechanism of action of these drugs, how they work and how they prevent protein synthesis. Now, because these drugs prevent protein synthesis, they are bacteriostatic in nature. We explained what bacteriostatic in nature is. They do not kill the bacteria. They hot, static means stop, so they simply stop the growth of a microorganism. They simply stop the growth of a microorganism, and therefore they depend on the immune system to clear the bacteria. So we cannot use them in a patient with a compromised immune system. Nor can we use them for very, very, very serious infection. Now, tetracyclines are quite broad spectrum. They're broad spectrum. Aminoglycosides are good for gram-negative microorganisms. Okay? Good for gram-negative microorganisms. Some of them, like amikacin, kanamycin, and streptomycin, are reserved for tuberculosis mycobacterial, the so-called TB. They are good for the TB mycobacterium. So practice these, and we'll see you